friends, welcome to the lecture. If you recall, in previous lecture we discussed some basic concept of ordinary differential equation, and in this lecture we will continue our discussion of ordinary differential equation. So, in previous lecture we have discussed the classification based on the dependent function. In fact, we have discussed what is linear differential equation and what is nonlinear differential equation. Now, in this lecture we discuss the classification based on the conditions provided to along with the differential equation. So, consider the following differential equation: y dash t plus alpha y t equal to 0. So, here this is a linear differential equation given to us. Here t is independent variable and t is a belonging to R, and which may represent the population growth model in a single species. Here we have already discussed that this represent a population growth model in a single species, and we may easily check that yt equal to c e to power alpha t, where c is an arbitrary constant, is a solution of differential equation 5. Here we get a one parameter family of solution. If you look at here, the solution is one parameter. So, you change your c, and here c is a constant, and if you look at this alpha is a parameter present here. So, we can say that this c, if you keep on changing this c, we have a different solutions. So, here we can say we can get a one parameter family of solution, and this one parameter family of solution consists of infinite many solution. And frequently we are interested only to find out one solution, because whenever we have a real world problem and we are formulating it as a ordinary differential equation, we only interested in finding a unique solution rather than having infinite many solutions. So, we are interested only to find out those solution of 5 which also satisfy certain other condition. Such conditions may be represented in terms of in several forms, but two of the important forms are initial conditions and boundary conditions. So, here we can say that these are initial condition and boundary conditions. There are several other forms are also available, but here we consider only these two. They are initial condition, they are nonlinear, non-local conditions, there are impulsive conditions, there are several other conditions available, but here we will consider restrict ourselves to initial condition or boundary conditions. So, what are these initial condition or boundary condition? Let us discuss this. So, we want to find out the population of the species at any given time t, provided that the population at time t naught was given as y naught. So, along with the differential equation, it is also given that at time t equal to t naught, the population is y naught. So, with the help of this, we want to find out the solution. So, if we look at this possibility that initial population is given as 0. So, it means that at time t naught, y of t naught is equal to y 0, and it is given that y 0 equal to 0. Then this implies that we have only c equal to 0, and this gives that we have population yt at any time it is coming out to be 0. How it is? If you look at, we have what? We have solution as yt equal to c to power alpha t. Now, it is already given that at time t equal to t naught, your solution the initial condition is given as 0. So, here we can say that y naught is equal to 0 equal to y t naught equal to c e to power alpha t naught. Now, this 0 is equal to c e to power alpha t naught. Now, e to power alpha t naught is never 0. So, c has to be 0. So, c has to be 0. If c is equal to 0, then solution is nothing but a 0 solution. So, in this case, when initial condition, when the condition given at t naught is coming out to be 0, then the population will remain 0 for all future time t. Now, if we consider the initial population as 1, we have y naught equal to 1, then we can check that c is coming out to be e to power minus alpha t naught, and the population will be given as e to power alpha t minus t naught. That also you can check here in place of here in place of 0, it is 1. So, if it is 1 equal to c e to power alpha t naught, then c is coming out to be minus. So, here if we consider y naught equal to 1 equal to c e to power alpha t naught. So, we can check that here c is coming out to be e to power minus alpha t naught. So, using this value we can write our solution as y t equal to e to power alpha t minus t naught. So, here if you look at, if your initial condition is changed from 0 to 1, then your solution is also changed. So, here solution is 0, here solution is y t equal to e to power alpha t minus t naught. Now, if initial point t naught is given as 0 and y 0 is given as y naught some value, then this c is coming out to be y naught, and we can say that the population is given as y t as y naught e to power alpha t. So, if initial population when initial time is given as 0, then solution is given as y t equal to y naught e to power alpha t. So, so here the solution, every time solution is depending on the initial condition. So, if initial condition the condition given at the initial point t naught is 0, then we have 0 solution. If it is some non-zero quantity, that is 1, then we have a solution like this, and if initial point is 0, then solution is coming out to be this. So, now look at the next example. Consider the following second order differential equation: y double dash plus p plus q y dash plus p q y equal to 0. So, this is an second order differential equation with the constant coefficient. Here p and q are constant. So, we can find out the solution of the given equation as y t equal to alpha e to power minus p t plus beta e to power minus q 2. Now, if the condition along with this differential equation is given as this: y 0 equal to 0 and y dash 0 equal to q minus p. Since it is a second order differential equation, we need two conditions. One condition given at 0 is 0, and one condition is given at 0 in terms of derivative. So, y dash 0 is equal to q minus p. We can simplify this and we can say that we have alpha equal to 1 and beta equal to minus 1. So, how we can look at this? So, here we have y t equal to alpha e to power minus p t plus beta e to power minus q t, and condition given as y of 0 is equal to here we have taken y 0 is 0 and y dash 0 is q minus p, it is 0, and y dash 0 equal to q minus p, and we want to find out the alpha and beta. So, here use this condition y 0 equal to 0, then it is 0 equal to alpha and e to power minus p into 0, it is coming out to be 1 only. So, alpha plus beta. So, 0 equal to alpha plus beta, and if you look at the y dash t is equal to minus p alpha e to power minus p t plus beta e to power minus q t, and if you differentiate this e to power minus q t, it will give you e to power minus q t into minus q, and now put y dash t as 0. So, this will give you q minus p equal to minus p alpha, and this will come out to be 1 and minus beta q. So, minus p alpha minus beta q is coming out to be this. So, we can write it this as alpha plus beta. So, here I can say that this implies that you can write beta as minus alpha. So, if you can write beta as minus alpha, minus p alpha, minus beta is coming out to be alpha. So, alpha q. So, here we can take out alpha and we have what? Q minus p, that is q minus p here. So, this implies that alpha is equal to 1, and if you look at this equation beta equal to minus alpha, then this implies that beta equal to minus 1, and that is what is written here, that alpha is equal to 1 and beta equal to minus 1. So, the particular solution satisfying the given condition is given as y t equal to e to power minus p t minus e to power minus q t. So, here condition is given at only one point, that is 0 here, and if you look at the previous example, here also condition is given at only one point, that is t naught here. Now look at the second example. Second example is this: consider the following differential equation for the motion of simple pendulum, and we already know that this is a very famous example of simple pendulum, and your equation is coming out to be y double dash plus y equal to 0, and we know that the solution is given as yt equal to alpha sin t plus beta cos t. Now here alpha beta are arbitrary constant, and t is from R. Now since it is a second order differential equation, we need two conditions. So if we consider the following two cases: first condition, if y0 is 0 and y pi by 2 is equal to 0, we can check that yt is coming out to be 0, and if y0 is equal to 0 and y pi by 2 is equal to 1, then solution is coming out to be yt equal to sin t. This you can easily check. When you put y0 equal to 0, what is given here? Here it is yt, just a minute, here it is y of t is equal to, this is yt equal to alpha cos of t plus beta sin of t. That is what we have written here, alpha sin t plus beta cos t. Anyway, here we have written in a different manner, but we need to find out the solution of this equation, provided that y0 equal to 0 and y pi by 2 is equal to 1 here. We want to find out the solution of this. So when you put y0 equal to 0, it will give you 0 equal to alpha cos of 0 is 1 plus beta sin of 0 is 0. So you will get alpha equal to 0. Now consider the second equation. It is y pi by 2 is equal to 1 equal to cos of t is basically cos of pi by 2 is 0. So it is alpha times 0 plus beta sin of pi by 2 is equal to 1. So this implies that beta is coming out to be 1. So we can say that the solution is given as what? Solution is given as yt equal to, now alpha is 0 and beta is 1, so solution is coming out to be sin t, in case then when y is 0 equal to 0 and y pi by 2 is equal to 1, which is given here, that if y 0 equal to 0 and y pi by 2 equal to 1, then yt equal to sin t. If you look at the first case, if y pi by 2 is equal to 1, in place of 1 if we write 0, then this second equation, this equation is replaced by the following equation, it is 0 equal to beta. So here this will give you beta equal to 0, alpha is already 0. So in this particular case your solution is coming out to be 0. So this is the solution when y 0 equal to 0 and y of pi by 2 is also coming out to be 0, and this is the solution when y of 0 is equal to 0 and y of pi by 2 is coming out to be 1. So if you change your condition, your solution will also change. And if you look at in example 1, in the previous example, conditions are given at 1 point, while in this example conditions are given at 2 different points. For example, it is 0 here and pi by 2 here. So in previous example your condition is given only at 0, and earlier one it is given only at t naught, right. So it means that in first example conditions are given at 1 point, while in example 2 conditions are given at 2 different points. So conditions given at the same value of t are known as initial conditions, right. So it means that if all the conditions are given defined only at 1 point, we call that problem conditions are initial condition, and the corresponding problem is known as initial value problem, while the conditions defined at 2 or more than 2 points, we call the conditions are boundary conditions. So here these 2 points are generally the endpoints of the interval. So in the case when conditions defined at 2, which are generally at the endpoint of the interval, or more different points, are called boundary conditions. So if along with ordinary differential equation, if the conditions are prescribed at only 1 point, it is a initial value problem. If along with ordinary differential equation, if the conditions are defined more than 1 point or say 2 point or more than 2 point, then it is known as boundary value problem, and conditions are known as initial condition and boundary conditions respectively. Okay. Now, let us consider the following remark. So, consider the following differential equation 2y dash whole square plus t square equal to 0. So, here if you look at whatever condition you define, this will not have any solution. Here if you look at, this is a nonlinear problem because your y dependent variable y dash is coming in terms of square. So, this is a nonlinear problem. So, it is a nonlinear ordinary differential equation, but here whatever initial or boundary condition you prescribe, this will not have any real valued solution. Now, if you look at the second remark, it says that an initial value problem may have no solution, only one solution, or may have more than one solution. For example, if you consider the initial value problem ty dash minus 3y plus 3 equal to 0. If we look at in A, B, C, we have the same differential equation ty dash minus 3y plus 3 equal to 0, and in A, B, C we are changing only the initial condition. For example, in A part it is y0 equal to 0, in B it is y1 equal to 1, and in C it is y0 equal to 1. So, here in all the three cases we have we have condition given only at one point, right, and the only thing is that values are changed. So, if you look at the first thing, the initial value problem ty dash minus 3y plus 3 equal to 0 along with y0 equal to 0 has no real solution. The initial value problem ty dash minus 3y plus 3 equal to 0 given with y1 equal to 1 has one and only one real solution, yd ideally equal to 1 of the differential equation. And if you look at this initial value problem ty dash minus 3y plus 3 equal to 0 along with this condition y0 equal to 1, then it will have infinitely many solution or more than one solution. And if we consider one more problem y dash equal to under root y, where y0 equal to 0, this will also have a more than one solution. And here I am not working it out right now, and this you may consider as an exercise to find out that indeed in these cases we have the corresponding results. So, here we have seen that an initial value problem, here if you look at differential equation is same, the only difference is the conditions given at one point. So, only conditions are changing, and we have seen that we have no real solution, one solution or more than one solutions. So, the conditions are playing very important role. The similar thing is also happening in case of boundary conditions. So, if you look at this y double dash plus mod of y equal to 0, if you look at this is a nonlinear ordinary differential equation. Here t is lying in this interval 0 to pi, and conditions are given as y0 equal to 0 and y pi equal to some a, where a is a constant. So, here if you look at conditions are given at 2.0 and pi. So, it is the case of boundary value problem. So, differential equation along with boundary condition. So, it is known as boundary value problem, or we write BVP. Then differential equation has infinitely many solution if a equal to 0, no solution if a is greater than 0, and a unique solution if a is less than 0. So, again this I give as an say exercise to verify whether this will have the result stated here, that it has infinitely many solution if a equal to 0 and correspondingly all other stated result. So, here we can say a boundary value problem may or may not have any solution or may have more than one solution under different boundary conditions. I may give you one hint for this particular problem. If you look at the solution is what, here we need to consider the case depending on this mod of y, right. So, here we have to consider the case when y is positive and y is negative. So, this is not only one differential equation, but it is a set of two differential equation. So, depending on this you try to consider these things. This is just a hint. Hint is that this is what? This is given as y dash plus y equal to 0 when y is positive, and y dash minus y equal to, sorry, y double dash when y is less than 0. So, taking these and involving your boundary condition, you may verify this. Okay. So, here what our purpose is to show that a boundary value problem will also may have infinite solution, no solution or unique solution depending on the boundary conditions. Similar thing we have already seen for initial value problem. So, here we say that why we want to discuss all these things, why we discuss these example, that we need some kind of theory to deal with these kind of problems. So, we can say that it is observed that differential equations are usually originated as an effort of creating a mathematical model for the motion of physical system. It means that given a physical system, if you want to study, we have various ways, but the most common way is to propose a theory, right, and once we have a theory, we try to write down the equations governing that theory in terms of mathematical terms, and most of the times it is coming out to be differential equation. So, we say that for example, cases are simple pendulum. If we consider the case of simple pendulum, your differential equation is coming out to be y double dash plus y equal to 0 after simplification, after assuming certain things, and simple spring mass problem, this also give rise to a differential equation. While modeling of the physical problem, we may use different physical approximation, and in result of this we may lead to different differential equation. It means that if we assume certain set of assumptions, we have a differential equation. For example, if you consider the simple pendulum, if we assume that sine of y can be approximated by y, it is coming out to be y double dash plus y equal to 0. It is a linear second order differential equation. But if we do not assume this assumption that sine y is approximately equal to y, then this is y double dash plus sine y equal to 0, some constant times sine y equal to 0, which is a non-linear ordinary differential equation. And we can say, we have already seen that linear and non-linear differential may vary in a very different manner. So, it depends on the approximation which give rise to the different ordinary differential equation coming out to from the same particular physical system. So, it is very important that a physical system may give rise to more than one ordinary differential equation if we change the set of assumptions. So, recall that the differential equation for the simple pendulum starting from an initial angle y naught is a nonlinear differential equation given as follows this. This is what I am talking about, that initially we write it like this. Then if we assume that sine y is approximated by y by assuming that initial angle is very small. In that case, we can say that and this is a simple equation, y double dash plus g by L y equal to 0. Right. Look at here, we want to use equation 8 to find the motion of the pendulum satisfying the initial condition y0 equal to y naught and initial condition initial velocity y dash 0 is equal to 0. And we may it looks very strange, but it is true that there is no methods available to solve the differential equation 8 in terms of elementary functions. But we already know that in real world a simple pendulum actually moves. It means that it is not it stops somewhere, it actually moves. It means that our mathematical model is useless because we are not able to solve this mathematical model in terms of elementary function. So, we can say that this particular mathematical model is useless and have certain problems with the set of assumptions, and we need to construct a new model for the same physical system so that the new model have some solution. So, this is one instance we want to consider, and also we have seen differential equation which may not have any solution, but these are very rare phenomena, or we can say that these equation may not be so important, and many physical systems are having real solution, whether a suitable whether a suitable mathematical models is available or not. So it means that this, look at this simple pendulum, we already know that it moves whether we have suitable mathematical formula or mathematical models available or not. For example, if you look at this model, then we may not have solution given in terms of elementary function, but if we consider this, then of course we have a beautiful theory to find out the solution in terms of elementary functions. So therefore, to construct a useful mathematical model, we need to know that whether it has a solution or not, right. Once we have mathematical model, first thing we want to consider whether it has a solution or not, and this is the existence problem. So it means that identifying the class of differential equation which admits solution is indeed a very important problem of mathematical theory, because once we have a mathematical model, if it does not have a solution, then that model is useless kind of thing. So we want to first consider the existence problem, and having condition about the existence of solution is not the only requirement that is desirable for a useful model. It means that once we have a solution, that may not be sufficient at all, because we want to find out a solution which satisfies certain conditions. That since the problem relating to differential equation are organized or originated from physical system and expected to have unique solution for the given set of condition. So given set of condition, we must have a unique solution. So that is also important. So there are many differential equations which do not have unique solution. We are not saying that those are not important, but we want to find out a unique solutions. So we refer this problem finding the conditions such that a differential equation should have exactly one solution, and this kind of initial conditions are considered as conditions sufficient for uniqueness problem. So we can say that finding the conditions such that a differential equation should have exactly one solution for a given set of initial conditions are considered as uniqueness problem. And along with this, we also want to see that one of the important property regarding the satisfactory model is that if the initial conditions or boundary conditions are slightly changed, perturbed, then we expect that the outcomes are also slightly changed. So it means that if there is a slightly change in conditions, then there is a slightly change in solutions also, and it is desirable that our mathematical model should also have this important property. It means that the solution of the differential equation depend continuously on the initial condition, and we refer to this property as continuity of the solution on initial condition. Why this is important? Because whenever we consider a mathematical model, it is coming from a physical system along with some assumption, and it may happen that while finding out that conditions or that differential equation, we may have some kind of equipment problem. So it means that rather than coming y naught, it may have some difference, say it is y naught plus some delta kind of thing, where delta is small enough. But if y naught has some solution and y naught plus delta has some other solution which is drastically different from the original solution, then we simply say that our mathematical model is not good enough. So for example, we can consider the following differential equation. We have y dash equal to y with the initial condition y 0 equal to 0, and we can simply find out the solution, and its solution is coming out to be yt equal to ideally equal to 0. But if we perturb this initial condition by a epsilon, so we simply write in place of y0, we have y0 equal to epsilon, and in this case where epsilon is greater than 0, and we can say that the solution of the perturbed solution problem is now yt equal to epsilon e to the power t. When y0 equal to 0, we have a ideally 0 solution, but when we have y0 equal to epsilon, we have yt equal to epsilon e to the power t. You can say that why these two are so different, but if you look at the trivial solution is a bounded solution, but the solution of the same differential equation with slightly perturbed initial condition will be unbounded. Means this is an unbounded problem, unbounded solution, while this is a bounded solution. If you take t tending to infinity, then this is going to be infinity as well. So we can say that in this case we have a bounded solution, but in this case we have a unbounded solution, but we have only perturbed our initial condition slightly. Epsilon is very small here. So here we can say observe that a slight change in initial condition change the nature of the solution. in maybe in a very drastic manner. So, here we can, if we want to summarize, here we say that thus a mathematical model of a physical system should have the following properties. First property is solution should exist satisfying initial condition. Second, there exists a unique solution. So, first is existence and second is a uniqueness solution corresponding to each set of initial conditions. So, if we have one set of initial condition, we have a unique solution. If we have another set of initial condition or boundary condition, we have another solution exist, and that is unique. And solution of the differential equation depend continuously on the initial condition. It means that if we change our condition slightly, then we have a slight change in solution. So, it means that solution will depend on the data in a continuous manner. The above set conditions are known as well posedness conditions for a mathematical model, and this is known as Hadamard properties for well defined well posed problem. And we say that a mathematical model having these property is called a well posed mathematical model. So, finding well posed mathematical model is a rare phenomena, it is not so common here, and even for well posed problems finding the solution in its explicit form is really very difficult. So, there are several equations whose solutions are not explicitly known, but they are very important in many areas of science and technology. For example, this particular y double dash plus pt y equal to 0, this looks very simple one, and it cannot we can show that this cannot be solved for a general choice of function pt. So, it means that if pt is any general, this equation may be solved for simple choice of pt. For example, if I take pt as 1 by t square, it is solvable, but if we take pt as sin t, cos t or some other thing, this may not be so easy to solve this, and sometimes it may have we cannot solve this problem in terms of elementary function. So, for these problems we study the nature of solution through analytical consideration. So, in these cases when we do not have a explicit solution or solution is not given in terms of elementary function, we try to look at the other method available which are known as analytical methods, and we want to find out the properties like existence, uniqueness, continuation of solution depending on initial data, boundedness, stability, periodicity, asymptotic behavior and all that, provided the nature and behavior of solution of these problems. So, here we stop, and we have discussed the classification of ordinary differential equation, and we have discussed certain examples where these initial condition boundary conditions are important to have a unique solution, one solution or infinitely many solution, and also we have seen that why we need a nice theory to deal these kind of problems. So, thank you for listening guys, thank you.